Alright, so now we've spent some time looking at the second method that we now have of solving linear systems, which was substitution. So now our two ways are substitution and graphing. We're just going to spend a bit of time practicing using substitution in the context of using word problems. So in general, whenever you want to solve a word problem involving a linear system, there's two unknowns. We're going to define our variables, create a system of equations, just like we did way back in lesson 4. And once that whole situation has been modeled and set up, we're going to solve the system using substitution like we did last lesson. Okay, so for starters, we're going to take you back to lesson 4 when we looked at the problem where someone was investing into two different mutual funds. Okay, so one fund earned 7% a year, the other 8% a year, and what we then was come up with two different equations: x plus y equals 1400, and 0.07x plus 0.08y equals 104. Okay, so now we're actually going to try and solve them. What I'd like you to do first, though, is try it on your own. Okay, so remember the main step for substitution. We want to first isolate a variable in one of the equations. You get to choose which one, but you want to make your life easier, so make an easy choice. And then from there, substitute, i.e. replace the other variable in the equation with what you've isolated for, solve the resulting equation, and then find the other variable from there. So again, try it on your own. Refer to your notes from the last lesson, your homework, if you're stuck. But once you're finished and ready to check it out, press play and we'll go through it together. Okay, so first things first, check your answer. You should have gotten $800 for x, $600 for y, which means in your conclusion you're going to write that they invested $800 in the first mutual fund at 7%, and the $600 in the second mutual fund at 8%. So to solve this, again, first step that I wanted to do was to isolate for a variable in one of the equations. So the first equation is way easier to work with. There's no decimals involved. So I could have, as for choosing between x and y, it's really the same amount of work either way. They're both coefficients of 1 on each one. I chose to isolate for x, but you may have done y, and I'll just change one thing about your step, but that's okay. So I subtracted y from both sides, which means that x is now equal to 1400 minus y. Once I've done that, I need to now replace that variable in the other equation with what I isolated for. So I isolated for x here, it's 1400 minus y, so I replace the x in the other equation with the 1400 minus y. Again, if you isolated for y instead, you'd be replacing the y, but other than that, you get the same answer in the end. So once we do this, you'll notice here the equation has only y's in it. So I just need to expand and simplify, collect all my like terms, and eventually solve for y. So you can follow through the steps here. I use distributive property, go through the bracket, collected my like terms, brought the 98 over to one side, divided by 0.01, and I got y being $600. Okay, so one of the things a lot of people forget when solving linear systems is that there's two solutions. There's an x value and a y value. It is a point of intersection that you're looking for. So once we have y, we're not finished. We have to find x. So what you then do is you go back to one of the two original equations, the one of your choice. I personally, again, in this case, would choose the first one. It's a lot easier to work with. And so there it is down here. And I sub my answer for y, $600, into there. So I get x plus 600 equals 1400, so x is $800. Okay, remember on a word problem on a test, you need to write a concluding sentence, so write your therefore statement with your solutions in there, and then you're good to go. Okay? So let's try another one. Okay, so Julie has $25 in loonies and toonies. She has 15 coins in total. How many of each does she have? Okay, let's just set up the equations first. So we're going to let loonies and toonies, right? Let's let L represent the number of loonies. And we'll let T represent the number of toonies. Okay, so we got to create our equations for this one. This is not one we've already set up in an earlier lesson. So we have 15 coins in total, so that should tell us that number of loonies plus number of toonies, i.e. L plus T, is 15. Okay, so that gives us one equation. For the other equation, we can look at the fact that we have $25 in total. So if we have $25 in total, where does that value come from? Well, we get $1 for every loonie and $2 for every toonie. Okay, this one, I don't actually need to write 1L. It's actually not necessarily proper math to write 1L because it shows poor communication. So I'm going to delete this L, delete the 1 here because 1L isn't changing anything, it just simplifies to L. So we have L plus 2t equals 25. Okay, so in the end now we have two equations, two unknowns. We can use substitution or elimination. I would like you to solve this one on your own. And when you get an answer, push play and I'll reveal it. And we'll go through the steps in case you made mistakes, you can see where you went wrong. Okay? Okay, so for your answer, you'll get 5 loonies and 10 toonies. So you can follow through the steps here, see if you made a mistake, you can see where you went wrong. So I just isolated for a variable. I chose to isolate for L in the first equation. T would have been just as easy, or I could have used L in the second equation. It doesn't actually matter. So I isolated for L in the first equation, so I subtracted T from both sides. So I wound up with L equals 15 minus T, and replaced the L in the other equation with the 15 minus T. So I simplified there, got all my like terms together, solved for T, and I got T equals 10. Okay, so 10 toonies, which is great. Put that back into the original equation, which tells us that L plus T equals 15. So L plus 10 equals 15, and you solve for L, and you get 5 loonies. So again, you have your solution, write a concluding sentence, and then you're off to the races, you're done. Okay, let's take a look at one more. This one's a little bit trickier to set up. I'm going to give you a chance here, so pause the video, read through the problem, try and set up as best you can, and push play and I go through it together. Okay, so all I've done right now is I've defined variables. So it's asking for how old Pat's dog is today. So I let that be my unknown. So I let X be the age of Pat's dog today. So put that in the chart here. And I also let Y be the age of Pat now. Which is also good information to know. So that can be our second variable. So in our chart here, so I've organized the two different people, well, two different living things, Pat and the dog. And the fact that we're looking at two time frames, one being now and one being 4 years ago. So if the dog's age now is X, 4 years ago the dog's age would be X minus 4, which means 4 years ago Pat's age would be Y minus 4. Okay, well, how does this help us? Well, right now it's telling us that Pat is 3 times older than her dog. So that means Pat's age, which we called Y, equals 3 times the dog's age, so we have Y equals 3x. Okay, that's my first equation. Okay, my second equation is telling me that 4 years ago she was 7 times older than her dog. So that means Pat's age 4 years ago, which is Y minus 4, Pat's age 4 years ago, equals 7 times the dog's age, and the dog's age back then was X minus 4. So it's 7 times whatever X minus 4 is in brackets. So there's a nice way of getting two different equations, and then once we have those equations, we can solve them using substitution. Okay, in fact, if you look at equation 1, we already have Y isolated. We have that Y being equal to 3x. So right away, without having to do any work, you can just replace the Y in the other equation with 3x. Okay, so I'm going to get 3x in there for Y. The rest of the equation stays the same. I'm going to distribute the 7 through the brackets up here, so I get 7x minus 28. Okay, and then I just need to solve. Okay, so subtract 3x from both sides. So I get negative 4 equals 4x minus 28. If I add 28 to both sides, I get 4x equals 24. Okay, which tells me that when I solve for x is equal to 6. Okay, and in this particular case I'm actually done, because normally you'd want to go and find the other variable, which in this case is y, Pat's age right now, but questions aren't actually asking for that. The only thing the question asks for is the age of Pat's dog today. So we define that to be x. We found x down here, so the dog is 6 years old. Okay, and you actually did problems like this back in grade 9. But you didn't have substitutions. What you did last year is right off the bat, when you saw that Pat was 3 times older than her dog, instead of even introducing a second variable here, you could have easily just, instead of having x, just having, well, 3x. Just jump straight into making that substitution step. Okay, and then instead of y over here, you would have had 3x minus 4. Okay, and it just would have been a different approach of going through it. So in theory, you'd actually never need to use a linear system for this one, because you did it back in grade 9. But really, you are just doing a substitution here when you replace that y with 3x. So that's where that comes from. Okay, so that's it. That's all. So the homework, there's a couple questions in the textbook to try that you should have already set up a couple days ago in Lesson 4's homework, and some extra practice there as well. Okay, so after this, we're going to look at the third and final way of solving a system, a method called elimination, and then we'll be set to get ready for a test. Okay, so that's it for today. Hope this made sense, and let me know if you have any questions.